In this reaction, we have a symmetrical alkene that can react with hydrogen iodide at either of the two carbons. Let me show you how this might work. Let's take this alkene and let's go ahead and show the pi bonding electrons attacking the hydrogen of our hydrogen iodide acid. And what we'll do is protonate the right carbon. So we add a hydrogen to the right carbon, and that gives us a secondary carbocation here. In the next step, we have iodide attacking the positive charge of the carbocation, and that will give us an iodine attached to the secondary carbon and a hydrogen attached to the secondary carbon, which is not drawn. So if we were to name this, it looks like we would name this 3-iodohexane. Now let's see what happens if we attack the other carbon. So let me draw my hydrogen iodide this way, and I'll draw the arrow sweeping to the left. From this mechanism, what we'll try to do is deliver the hydrogen to the left carbon of the alkene, and we have a positive carbocation on the right carbon, and that's also secondary. So these two are equivalent in stability. So just looking at these, we can't say which one's more stable or not. Now, they're actually equivalent. Let me show you why. Now, this iodide here can attack the positive charge of the carbocation, and then what that gives me is iodine attached to the secondary carbon. So if I were to name this, remember we always number from lowest to highest to position the substituent at the lower numbering. This would also be called 3-iodohexane. So in summary, it does not matter which of these carbons receives the hydrogen, because they would both give a secondary carbocation. In addition, because of the symmetry of the molecule, it really doesn't matter which receive the hydrogen, because iodide is going to attack that third carbon in terms of the way we number the system.